Thank you all for joining me this morning. I'm really excited to share with you all kind of a culmination of my research from the past 2 years since I've been working on my master's degree, kind of following floating surface skimmer flow rates for sediment basin and also post-construction applications. So to kind of give you a little bit of a roadmap of what I'm going to be talking about today, kind of going to start with some background and motivation for this project, and then go into the kind of central research objective of this project. Go into a little bit more background from the literature review that was conducted, kind of then head into some means and methodology, go into our flow rate analysis, and then our skimmer sizing tools that were developed, and then kind of close out with some overall key takeaways with our conclusions and recommendations. So, we have a problem in the United States. So, as of 2022, over 50% of our assessed waterways throughout the US have been designated as impaired, meaning that they don't meet standards for drinking water, supporting aquatic life, or also recreational use. So this can be really attributed to non-point source pollutants such as sediment, metals, oil and grease, nutrients, or pathogens. So these are intercepted by stormwater runoff and are subsequently deposited into our downstream waterways. So pollutant loading in these water bodies can really be attributed to the rise of urbanization, which increases in which causes increases in construction activity, and also impervious surfaces. So our construction activities are really susceptible to erosive forces due to activities such as land grading, excavation, and vegetation removal. And so as a result, we have a lot of exposed soil, which can be displaced by rainfall. And so these dislodged soil particles can then be intercepted by our stormwater runoff and then carried off-site. And now, on the other hand, our impervious surfaces can increase our volume and also flow velocities of our stormwater runoff, which this in turn will limit our infiltration capacity, and then can also increase our erosion potential. So one other thing to note, our stormwater runoff can also intercept a lot of these pollutants that I mentioned in the previous slide as it is flowing across these impervious surfaces. So to kind of combat these, we have stormwater control measures. So these are used to really mitigate the damage caused by our erosive forces and really ensure compliance with our environmental regulations. So our stormwater control measures effectively slow, treat, and manage that stormwater runoff so it's not migrating into our downstream receiving water bodies. So the U.S. Environmental Protection Agency's National Pollutant Discharge Elimination System, it establishes a permitting system that provides specifications for our acceptable pollutant levels that can be discharged off-site. So these permits cover stormwater discharge from a variety of sources, including those construction activities and also municipal sources. So erosion sediment control measures fall under these active construction site. They're used for active construction sites, and these fall under the construction general permit. Whereas our post-construction stormwater control measures, they fall under the municipal separate storm sewer system permit. So this leads us into our research objectives. So the primary objective of this research was to really investigate how various configurations are influencing the discharge rates and overall performance of floating surface skimmers designed for use in either sediment basins, on active construction sites, or post-construction detention and retention basins for those uses. So this was completed in 4 tasks. The first task was to conduct a comprehensive literature review on skimmers as dewatering mechanisms, the importance of properly sizing skimmers for those applications, and also kind of assessing previous performance. That second task was to perform controlled testing of various floating surface skimmer performance at the Auburn University-Stormwater Research Facility. Our third task was to analyze our experimentally collected flow rate data to create models to help predict flow rates at given depths. And then our last task was to develop a interactive and user-friendly skimmer sizing tool to kind of help provide guidance and facilitate simplifying the process of selecting an appropriate skimmer size for implementation. So kind of going into some more background here. So sediment basins are temporary structures that are installed on construction sites as a sediment control measure. So they're used to capture, temporarily detain, and also treat sediment-laden stormwater before it is eventually discharged off-site. These sediment basins using sediment control systems have been found to remove up to 98% of suspended sediment after rainfall events. So our sediment basin efficiency is influenced by several design parameters, including size, geometry, using energy dissipators, sediment characteristics, and so on. So our sediment design and performance can also vary by jurisdiction due to the soil properties on site, as well as the frequency and severity of our precipitation events. The minimum volume a sediment basin should be able to accommodate is either 3,600 cubic feet per acre or the volume from the local 2-year 24-hour storm event. It's really important that sediment basins are properly designed on our construction sites so that we have enough storage volume available for capture after our rain events, while also allowing for some sufficient time for sedimentation. So this is a diagram of a sediment basin provided by IECA. So to kind of give you a quick little rundown, we have our bore bay, which is kind of our localized area that's used for really removing those heavier soil particles. And additional practices such as check dams or excavated sumps can also be used to kind of help slow those flow velocities going into that sediment basin. We then have our stabilized inflow channel, which is our conveyance channel that can help direct runoff into the basin without causing any further erosion. Our porous baffles, which are our energy dissipators, these effectively kind of spread the flow out over the width of the basin for increased deposition of our suspended sediment. And then we have our dewatering mechanisms such as a floating surface skimmer, a riser structure, or a auxiliary spillway. So our sediment basin dewatering is the process where captured stormwater runoff is slowly released off-site after required detention times have been met. So dewatering in a sediment basin has a 2 to 5 day requirement so that we're ensuring sediment basin functionality. So to allow for greater control of this dewatering, principal spillways, as I mentioned, riser structures, auxiliary spillways, and also floating surface skimmers have been adopted to really improve the quality of our water that's being discharged from sediment basins. So this brings us into floating surface skimmers. So floating surface skimmer is a device that sits at the water surface and then decants from the top of the water column. Throughout reviewing the literature, we have found that several studies have really verified that skimmers are really one of the most effective practices used for sediment basin dewatering. Couple of advantages that floating surface skimmers offer: they allow for greater control of available storage in our sediment basins. They increase time for sedimentation since that water is being discharged from the top of the water column. It minimizes the amount of total suspended solids being discharged from the sediment basin. And another cool thing is they can also be reused on future projects. So skimmers have also been shown to really consistently outperform our traditional dewatering mechanisms in terms of reducing our sediment present in the effluent from a sediment basin. So studies have shown that skimmers can have a sediment retention efficiency of up to 97 to 99%. And another study indicated that a perforated riser structure, one of those more kind of traditional dewatering mechanisms, had a sediment loss of almost 2 times greater than that of a skimmer, meaning there was almost 2 times the amount of suspended sediment present in that effluent than a skimmer. And so with these advancements, the construction general permit really currently mandates that an outlet structure and a sediment basin must dewater from the top of the water column. Um, Even though we've shown that skimmers can be really effective in controlling the dewatering of sediment basins, they have to be properly sized to meet these detention requirements. So the size of the skimmer is based on the size of its inlet. It's also really increasingly common for manufacturers to provide customizable orifices or inlets to allow for even greater control over these discharge rates. So when we're designing a sediment basin and a dewatering mechanism on a construction site, that skimmer design is based on the sediment basin detention requirements. So the required skimmer size will be calculated using the required discharge volume from the sediment basin as well as the detention time. So there are a wide variety of skimmers available on the market, and skimmer flow rates can differ across manufacturers, and they're not solely based on the inlet size. So each skimmer has its own design, which can affect the hydraulic performance. And so, as in addition, theoretical or calculated flow rates can also lead to errors in estimating dewatering times. So there's a need to have really accurate flow rates for our skimmers, which can only be determined through experimental testing. And our accurate flow rates really improve selection guidance and ultimately increase our sediment basin efficiency on those construction sites. So, kind of more on the post construction side now, we have detention and retention basins. So, these are a widely used post construction stormwater control measure to kind of help mitigate flooding in urbanized areas and also kind of help with downstream pollutant loading in receiving waterways. So, the primary function of these is to reduce runoff volumes and also minimize those peak flows from storms. And both detention and retention basins treat runoff by allowing pollutants to settle out from suspension, kind of similar to a sediment basin on a construction site. So these are commonly dewatered through an outlet pipe, a riser structure, or spillway. And so there's really an opportunity for skimmer applications in these detention and retention basins to kind of help increase capture of these suspended pollutants while also providing greater control over the available basin storage. So this leads us into our means and methods of my study. So our testing was conducted in the skimmer evaluation apparatus at the Auburn University-Stormwater Research Facility out in Opelika, Alabama. This tank is a refurbished steel roll-off dumpster that was donated to us, and it has been sealed so that it's watertight. The depth of the skimmer tank is about 7 feet, and the approximate volume is about 1,053 cubic feet. This tank features 2 flanges at the bottom of the south wall, an 8-inch and a 4-inch flange, where water is able to be discharged. And all of our skimmers that were tested were installed on the 8-inch flange. So, to give you a quick tour of the skimmer tank, in the left photo, we have our access ladder so that we could get in and out. We also have the measuring tape adhered to the wall so that we could take manual measurements throughout testing. And then at the bottom of the access ladder, we have our little PVC pipes, and that's where our level logger would go in. And a level logger is our pressure sensor, and it would measure the change in water depth as the skimmer is draining the tank throughout a test. On the right side, we have our water delivery system. So water is pumped in using 4-inch pumps from the detention pond at the top of the picture. And it's pumped in through these PVC pipes that are kind of outfitted in a T configuration. And they're outfitted that way and kind of propped up against the wall to kind of minimize buoyancy effects as water is being pumped into the tank. So here's an example of a skimmer installed in the skimmer tank. We have our flange that I mentioned earlier. This is where water is being discharged through the outlet, and it will go back to that detention pond that you saw in the previous slide. We have our flexible hose that allows for proper flotation as that skimmer is going, as the water levels increase and also decrease as the tank is being filled and drained. Our barrel, which is our drainage pipe where the water travels as it enters through the inlet. The head or the float, which provides flotation and allows for that skimmer to kind of stay at the water surface. Our ventilation pipe, which provides an opening to atmospheric pressure, and this helps prevent a vacuum from forming and also to really kind of ensure consistent flow coming in from the orifice or inlet. We then have a metal screen, which helps prevent debris from entering the inlet, and the inlet is behind that metal screen. So throughout testing, a total of 13 skimmers were evaluated. So 8 of those skimmers were designed for use in sediment basins. So as I said, the size of the skimmer is based on the size of its inlet. So our sizes range from 8-inch all the way down to 1.5-inch. Our 8-inch skimmer has an 8-inch diameter inlet. Same goes for our 1.5-inch skimmer has a 1.5-inch size inlet. So each of these skimmers was made using Schedule 40 PVC pipe, and each of these skimmers have a circular orifice. So what we were evaluating for these sediment basin skimmers was the application of an adjustable slider. So 4 slider configurations were tested on the 5 largest skimmers: 100%, 75, 50, and 25%. For the 3 smallest skimmers, that 25% configuration was omitted just due to those skimmers' small size. It was deemed that it wouldn't really have any meaningful application. And so on the post-construction side, 5 post-construction skimmers were evaluated here. And these post-construction skimmers can be kind of further categorized into kind of 2 groups. So in this slide, you can see these are our larger post-construction skimmers. All of our post-construction skimmers were made out of a chlorinated polyvinyl chloride pipe and a high-density polyethylene pipe. So our large post-construction skimmers are 8 inches and 4 inches in size. And as you can see here, these also kind of have a different design than the sediment basin skimmers. And the big thing to note about these is they were tested with and without that ventilation pipe. So we could kind of evaluate different flow conditions there. So these skimmers, instead of a circular orifice, they have a rectangular inlet. And so our inlet size was configured using removable plates. For our 8-inch post-construction skimmer, we evaluated 100%, 75, 50, 25, and 1% inlet openings. And for our 4-inch skimmer, we evaluated 100%, 70%, 50, 30, and 1% inlets. And these photos here are a couple of examples from the 4-inch skimmer. So for our 3 smaller post-construction skimmers, these have kind of the same design as our sediment basin skimmers, but they're approximately 5% heavier because of the materials used. These also, like our sediment basin skimmers, have a circular orifice, and these were evaluated using an adjustable slider. So 3 slider configurations were tested for these: 100%, 75, and 50%. And all of these were tested with that ventilation pipe. So testing followed an enhanced version of the ASTM D8107 standard. And those enhancements just come from an expanded kind of apparatus depth, and also expanded kind of data collection measures, so the use of that level logger. And so the testing protocol was very simple. The first thing that we had to do was configure our skimmer, so configure the inlet or the ventilation pipe, depending on what was being tested. We would then either block the inlet, or depending on the size of the skimmer, we would raise it up out of the tank using our mini excavator, so that water was not flowing through as the tank was being filled. We then filled the tank, and then once the tank was full, we would kind of unblock or lower the skimmer down and allow it to drain the tank. So each of our configurations were tested in triplicate to kind of assess repeatability and also address any measurement of uncertainty. So a total of 87 tests were completed for both the sediment basin skimmers and the post-construction skimmers. So 174 tests in total were evaluated across all of our skimmers that we tested. And here's kind of a quick little video of the start of a test. This is the 8-inch sediment basin skimmer, kind of as it's starting to drain the tank here. So moving on into our flow rate analysis. So our flow rates were calculated using the skimmer tank dimensions, as well as the change in depth every 10 or 15 seconds, depending on that skimmer size. So our plots showing flow rate as a function of depth were developed to really observe skimmer behavior throughout a test. So this graph that you can see on the right is showing our 8-inch sediment basin skimmer set to 100% open. And this graph, as I said, is read left to right. So it starts at our greatest depth and then goes all the way down to our 0 depth, and our flow rate kind of decreases from there. So triplicate tests for our configurations were plotted together for comparison. And so from there, now one thing to note is that this is the same, our plots here are the same graphs from the previous slide. So for all of our sediment basin skimmer configurations, a similar trend was observed, and they could be kind of divided into two approximate linear sections, and those are labeled as Zone 1 and Zone 2. So Zone 1 reflects the section where that flow rate is kind of sloped and decreases down to 0, and Zone 2 is the section that starts at the greatest depth until that distinct turn is kind of observed, where the flow then kind of transitions into Zone 1. So that transition point between Zone 1 and Zone 2 was chosen arbitrarily for these, just for time and ease. And the plot was divided into these two sections really for modeling purposes, and to also kind of better portray flow behavior, particularly in that Zone 2 section, which really accounts for most of the dewatering time and is also most applicable to real-world performance. So the linear equation was extracted from the Zone 2 section and was used to create a model to predict those flow rates at a given depth in the tank. And then using that linear equation from Zone 2, as well as that chosen transition depth, a new slope was calculated to model Zone 1 to really ensure that flow rate is going to 0. So going into our flow rate results. So once all of our slider openings were tested for each skimmer, those data sets were combined to examine differences in skimmer behavior across all of our slider configurations. So here we have our flow rate models that we made for each skimmer size. These show the model for each tested inlet opening for a given skimmer size. So our 100% flow rates are in orange, 75 is in navy, green is 50, and then that kind of brown is 25%. Here in this slide, we have our 8-inch and 6-inch skimmer results. And in these tables, we have our transition depths chosen, as well as the average flow rate for each slider opening, as well as the previously published flow rates by the manufacturer. And this previously published flow rate only applies for the 100% open configuration. So for our 8-inch skimmer, our previous flow rate here was close to 98,000 cubic feet per day. Our experimental maximum average flow rate here was about 92,600 cubic feet per day, and that lowest was close to 15,000 cubic feet per day. For our 6-inch skimmer, our manufacturer's flow rate was about 52,000 cubic feet per day. Our experimental average flow rate was close to 53,000 cubic feet per day, and our 25% was close to 11,000 cubic feet per day. Moving into our 5-inch skimmer, our manufacturer's previously published flow rate here was close to 33,000 cubic feet per day, which was a bit higher than our experimental maximum average flow rate, which was kind of close to 31,000 cubic feet per day. And then our minimum here was close to 8,000 cubic feet per day. For our 4-inch skimmer, about 20,000 cubic feet per day for the manufacturer. For our experimental max, it was about 19,000 cubic feet per day, and our minimum here was close to 4,000 cubic feet per day. For our 3-inch skimmer, manufactured here closer to 10,000 cubic feet per day. And here it was kind of closer to 9,500. And that minimum here was close to 2,300 cubic feet per day. For our 2.5-inch skimmer, this is where that 25% opening is now omitted. Our manufacturer here, about 62,000 cubic feet per day. Experimental max was 6,600, and our minimum here was about 3,400 cubic feet per day. Last two, our 2-inch skimmer manufacturer was close to 3,300 cubic feet per day. Our experimental max was close to 3,900 cubic feet per day, and that minimum about 2,400 cubic feet per day. For our 1.5-inch, our manufacturer was closer to 1,700. Our experimental was closer to 1,800. And finally, that last minimum flow rate here was close to 1,000 cubic feet per day. So after all this was said and done, we decided to create a visual representation to kind of distinguish how these flow rates overlap amongst all of these skimmer configurations for all of our skimmer sizes. So on our y-axis here, we have our flow rates, and then on the x-axis, we have all of our skimmer sizes that were assessed. That red dotted line is that previously published flow rate, and then the solid black lines are labeled for each slider configuration that were tested. So just to kind of show the overlap amongst all of these skimmer sizes here. So now going into our post-construction skimmer flow rate modelings. Now, our post-construction skimmer behavior across all our evaluated configurations and sizes didn't necessarily follow that kind of nice, distinct two-zone, approximately linear pattern. So we kind of employed some alternative analysis methods to develop these flow rate models. Based on these trends that we observed in those flow rate depth plots, one of 3 models were chosen to fit the data. A 2-section segmented regression model, a 3-section segmented regression model, and a hill-type saturated model. And these models were used really as well a robust method for kind of modeling these flow rates as opposed to dividing kind of a little more arbitrarily these experimental data sets into 2 or 3 sections. So our 2-section segmented regression model was used for plots that could be divided into 2 approximately linear sections, like our sediment basin plots. So the key thing about these are, instead of visually determining where that breakpoint is between zone 2 and zone 1, that breakpoint was calculated using the regression model. For our 3-section segmented regression model, this was used if a plot kind of indicated 3 approximate sections. And so what we did here was we actually did 2-section models that were overlaid to create that 3-section model. So we have our zone 1 and zone 2 that I've explained, and then we also have a zone 3, which is that last kind of little arm hanging down at those greatest depths here. So what we did to start was we created our zone 1 and zone 2 model, and then from there created a zone 2 and zone 3 model, which were then, those models were then overlaid to kind of verify the continuity. And so in this chart here, the bottom graph, that solid line represents the zone 1 and zone 2 model, and the dotted line reflects the zone 2 and zone 3 model. So once everything was overlaid and verified, what we ended up using was the zone 1 and zone 2 model, and then only that zone 3 section from the zone 2 and zone 3 model. for that final model. And then finally, for our hill saturated model, this was used to fit data if flow rates kind of exhibited a plateau at greater depths, and then a gradual transition was observed in the flow pattern rather than kind of a distinct breakpoint, as we've seen previously. So going into those results, again, once all our models were developed for all of our configurations for a given size, they were all combined to kind of examine trends in skimmer behavior across all of our inlet openings. And here we were really looking more at the maximum flow rates that these skimmers could achieve rather than the average flow rates. And the other thing here is these are in cubic feet per second instead of cubic feet per day. And for our 8-inch and 4-inch skimmers, the vented and unvented configurations were compared. So for our tables, we are describing our model types that we used, as well as the transition depth, if that's applicable. Then we have our maximum observed flow rate, and then our maximum model flow rate. And now the one thing to note about the maximum model flow rates is that across the board, all of these models, the maximum depth here was 6.3 feet, just for uniformity sake. So starting with our 8-inch skimmer, for our vented configuration, we have 2 section model types used across the board, except for that 1% inlet opening, which a hill type was used. For unvented 8-inch skimmer, we used hill type models for 100% through 50% inlet openings, and then 3 section models for the 25% and 1%. Now, one thing that we saw here was that our maximum flow rates for the unvented configuration were greater than the vented configuration. So for our unvented, our maximum flow rate that we saw here was close to 3 cubic feet per second, whereas for our vented configuration, our max flow rate was about 2.6 cubic feet per second. Going into our 4-inch post-construction skimmer, here we use 2 section models for the 100% and 75% openings, and then 3 section models for the 50% down to 1% inlet openings. For our unvented configuration, we used hill types for our 100% and 75% inlet openings. For our 50% inlet opening, we kind of noticed a kind of interesting flow pattern here. We saw a horizontal section kind of at greater depths, and then a jump occurred. And then from there, we used a 2-section model to model that. And the reason we believe this happened is the skimmer kind of stabled out at around 4.2 feet here, and kind of experienced better airflow there. But for our 30% and 1% openings, we use 3-section models for those. And again, our unvented configuration flowed faster than our vented configuration. So our maximum observed flow rate here was close to 0.8 CFS, whereas our max observed flow rate for our vented configuration was closer to 0.6 CFS. And so overall, for our vented configurations, flows generally were slower here, but they were a little bit more stable and predictable. And the reason for that being, we have that ventilation pipe that opens our flow up to the atmosphere, so it kind of simulates more open channel flow conditions. And on the other hand, our unvented configuration, those flows were generally faster, but they were a little more erratic, a little less predictable. And so for these, we saw kind of more siphoning effect. So our flow wasn't really regulated since it wasn't opened up to the atmosphere. So this skimmer kind of just sucked in and chugged water, and just was pulling it out a lot faster. So going into our smaller post-construction skimmers now, just a reminder, all of these were tested with the ventilation pipe, and these had that circular orifice here. So for our 3-inch skimmer, for 100% open, we used a 3-section model. And for the 75% and 50%, we used two section models. And our max observed flow rate here was about 0.2 CFS. For our 2-inch skimmer, we used two section models across the board here for all of our inlet openings. Our maximum observed flow here was about 0.1 CFS. And then finally, for our 1.5-inch post-construction skimmer, we used two section models for the 100%, 75% inlet openings. And then for that 50%, we also saw that kind of horizontal section. And then the two section model was used after that jump occurred. And our maximum flow rate here was close to 0.1 cubic feet per second. So now kind of moving on to the skimmer sizing tools that were developed. So once our testing and analysis were completed for all of our configurations, our flow rate models were used to create some interactive and user-friendly skimmer sizing tools to kind of help offer some design guidance. So two sizing tools were ultimately made for both the sediment basin skimmers and the post-construction skimmers. And so they're very similar here. So one was kind of geared more towards engineers and the other geared more towards estimators and designers. So what you're looking at right here is the engineer's calculator interface. This calculator really describes the stage storage relationship occurring as the skimmer is dewatering a sediment basin. So here the user will input the skimmer size, slider opening, skimmer start elevation, as well as some target maximum and target minimum dewatering time. On the kind of sediment basin side, the user will input an elevation for each stage, as well as a corresponding surface area. And using this information, the tool will provide an incremental storage volume, available storage volume, as well as the dewatering rate at each stage. And then we have an incremental dewatering time and a cumulative dewatering time. Now, cumulative dewatering time, the total will appear in that green cell that you're seeing. So if that cumulative dewatering time falls within range of our maximum and minimum target dewatering times, that cell will be green, as you can see. If that time falls out of range, that cell will turn red. The tool will also provide an average flow rate, and it will also provide kind of a chart describing that stage storage relationship over time, just to kind of provide more of a visual summary of our results. So moving into the estimator's calculator, this is much simpler than the engineer's calculator, and it's based on also sediment basin volumes. So the user has the option to input a known sediment basin volume, or they can calculate it if it is unknown. So at the top interface that you can see, this is if the user knows their sediment basin volume, whereas on the bottom interface, the user has the option to input parameters such as the bottom length, bottom width, the depth, as well as the side slopes, and the calculator will provide the basin volume. The user will then input the time to dewater, and then from there, the tool will provide the skimmer size, the inlet opening, as well as the previously kind of published equivalent skimmer size and also orifice size from a previous design from this manufacturer. And the last thing that this tool will provide is the average flow rate of the skimmer that it provides. So for the post-construction engineer's calculator, very similar to the sediment basin calculator, with a couple of modifications and improvements. So the units in this calculator is in cubic feet per second, again, not cubic feet per day like the other one is. One of the biggest improvements here is that the user can select top elevation, and instead of having to manually go in and put in each elevation at each stage, the tool will fill that in automatically. But the user will still have to go in and fill out the corresponding surface area at each stage. So also the skimmer start elevation here was removed to kind of avoid any confusion, and it was deemed unnecessary from the previous calculator. One other addition here is that we provide the max flow rate here for our post-construction skimmers. So for the estimator's calculator on the post-construction skimmer side, still allows the user to choose if the basin volume is known or unknown. An additional step here is that the user has to input the basin depth, which is then used to determine the number of actual days the skimmer will take to dewater based on our experimental data. So here, the tool will provide, again, the skimmer size, the inlet, as well as the maximum flow, that overall average flow rate, and the actual time to drain the basin. And one other really cool improvement that was made to this calculator is it provides the average flow rate for each day based on that actual time to drain. And this is to kind of provide the user to kind of show how that skimmer is performing across several days in the basin. So to kind of wrap up with some key takeaways. So experimental testing is really the most reliable way to determine skimmer flow rates. And so here we evaluated 13 different skimmers across 59 total configurations for sediment basin and post-construction basin applications using the skimmer evaluation apparatus at the Auburn University-Stormwater Research Facility. Using our experimental data, we developed flow rate models to predict flow rates at given depths below 7 feet for the skimmer tank. And then from there, using our models, we created a total of 4 skimmer sizing tools for engineers and designers to kind of help facilitate appropriately sizing a skimmer to meet their needs. A couple of future studies for this work would be to kind of evaluate other skimmer types from different manufacturers to kind of compare the skimmer performance across the board there. Also evaluating pollutant removal efficiency of these skimmers, and then testing the dewatering rates as the tank is being filled. Our methodology would be considered kind of more conservative since in real world conditions, the skimmer would be draining as the sediment basin or post-construction basin is filling as runoff is coming in. Here, the barrel is empty. So kind of evaluating how performance changes as the skimmer tank is being filled. And then also determining kind of different flow rates, how that changes across various temperatures. And with that, thank you all so much for your time. I really appreciate you coming to learn more about skimmers this morning, and I am happy to take any questions that you may have at this time.
Yes, thank you so much, Caroline. That was very informative. I will open the floor to questions. Like I said in the beginning, you can use the Q&A feature, or write your question in the chat, and Caroline will be more than happy to answer some of those. But I have a question for you, Caroline. When it came to like testing the skimmers, were there any skimmers that performed totally differently from what you had expected, them to do?
Yeah, definitely. So, my first kind of phase of testing was the sediment basin skimmers. So I was very used to that. And so when time came to test the post-construction skimmers, it was very interesting to see kind of the change in how those skimmers performed compared to the sediment basin skimmers. Especially since it's kind of hard to tell how each skimmer performs differently just based on visual observation during a test.
Hmm.
So going into that flow rate data and seeing all of those different shapes that I kind of showed earlier when I was showing the different flow rate models, I didn't know what to expect, but
Yeah.
it it wasn't really that, I guess. So
Yeah. Great. We have a question here from Joel Landers. He's asking, did you test any Marley skimmers?
I did not. And I think I think that would be a really great thing to do in the future, to kind of compare the skimmers that were evaluated in this study, especially because, since I mentioned earlier, the design of a skimmer, the hydraulic performance changes based on design. So I think that
Right.
would be a really great future study there.
Right. Our next question is from Derek Hutton. He's okay, so it's two parts. Did you have a reason for the break in the skimmer flow rates? And then he said about 1 foot depth. And then the
Mhm.
second question is, would the flow rate with different orifices, sizes be different with sediment-laden flow?
So, to answer the first question, the reason for that transition um, is so when the skimmer is kind of at, well, so when the tank is at max capacity, the skimmer, um, typically that barrel or the orifice is completely submerged. And so the barrel is full of water. And as the skimmer kind of is starting to drain the tank, and as it especially kind of gets towards the bottom, so kind of that 1 foot area, that barrel is kind of filling with air a little bit more. And so the flow pattern changes, which is really why that's occurring, in theory. And then to answer the second question, I think the flow would change with sediment introduced, which I think would also be a really great future study. I think the dewatering rates would probably be a little bit slower, just with the presence of suspended sediment in there, and viscosity and such. But again, another great future study right there for sure.
Right. Um, that's all the questions I see in the Q&A. I kind of wanted to also ask about the sizing tools. You may
Yeah.
have mentioned this, but where can engineers be able to find the tools to use them?
So these sizing tools are currently available on the Faircloth Skimmer website.
Okay.
So
Thank you for that. So,
yeah,
we engineers in the chat, want to test these out, like please go to faircostskimmer.com. I'll also include it in the follow-up email just in case any of you guys want to have access um, to those sizing tools. Any final questions, comments? We have Bill Klepak in the chat that said, great info. Thank you.
thank you.
Really was a great presentation to follow. If there are no other questions, I think we'll go ahead and end the webinar here. As always, you guys will get a follow-up email from Auburn Stormwater, and that will include your link to be able to download the PhD certificate, as well as a link to a YouTube recording of this webinar for you guys to kind of review afterwards. Thank you everyone for joining us. Next month, we will be having Shalane Berguis from ADEM to join us for TigerStream episode 24. So please be on the lookout for that email so that you guys can get registered on that. But apart from that, thank you so much for joining us, and everyone have a great day. Thank you, Caroline,
Thank
again.
you so much.
All right, bye.